afternoon, everyone. Thank you for joining us this afternoon for our Football Fridays at the On the Sidelines lecture with Peter Burns. He's going to be today talking about the future of energy and the Center for Sustainable Energy. So first, I'd like to introduce Peter Burns. He's the Henry J. Massman Chair and Professor of Civil and Environmental Engineering and Earth Sciences. He's been here at Notre Dame for 18 years, but he hails from Canada, so you can ask him a bit about that. He is currently the director for the Center for Sustainable Energy, director of the Material Sciences of Anticides, Energy, and Frontier Research Center. His research focuses on nanoscale control of anticide materials, and I've also been told that he's an avid car collector, and that he has a two-story garage of collecting cars that actually has a lift to lift them up to the second floor, so he'll have to share that with us. But first, welcome Peter Burns, and thank you for sharing your research with us.
Well, thank you. Thank you, everybody, for coming out to hear what I have to say about the future of energy. What I'm going to talk about is not so much the future as painting a picture of where we are today, how we got here, and then what challenges we face. I wish I had all the solutions for the future, but in fact, well, I don't. But through engineering, science, policy, ethics, etc., research, hopefully we'll move towards those solutions as time moves on. So first, I wanted you to just start by thinking about what your world would be like in the absence of energy, or at least in the absence of abundant, cheap energy that we live with today. So the most obvious thing that comes to mind is how you got here today. You could walk, you could take a canoe, or you could ride a horse. In the absence of abundant petroleum, those would be about your only choices. The lighting in this room and in your homes, all driven by electricity produced in a plant somewhere by consuming some sort of a fuel. I find the history of lighting in itself is rather interesting, and in many ways it parallels the use of our energy resources in our society. So if you think back, I don't remember 500,000 years ago, but if I did, I'd probably be sitting around a cave like Peking Man, or maybe even sitting around a fire in a cave, or even longer ago than that, something over 1 million years ago, Australopithecus would have been sitting around a fire. It wasn't really until the 1800s that light started to enter what you could think of as maybe the modern age of lighting. Before then, it was just candles and things of that nature. Gas street lighting appeared in the Pall Mall in London in 1820. Kerosene lamps were developed in the 1860s. The Pearl Street Station in New York opened its first electric service in 1882. And in the 1980s, complex fluorescent bulbs that we all know came onto the market. So there's been a huge change in the availability and the cost of lighting and energy in general. This is a study that was done now, I think 20 years ago, but it's a study of the cost of lighting. And I like it because it says a lot about the cost of energy in general. So here's time going from around 1800 to around 2000. Here's a light bulb. Let's say it's a 1,000 lumen light bulb, so that's probably roughly a 100-watt light bulb. Today, it would cost you approximately 1/10 of a cent to light this light bulb for an hour. So all the lights in this room together for my lecture, looks like there's quite a few bulbs up there. We might be getting into, 20 or 30 cents. One of those light bulbs in 1800, of course you couldn't light it with electricity, but to produce the same amount of light, you would have had to consume around $5 an hour. So to light this room would have perhaps been $100 an hour equivalent. It's kind of hard to imagine how inexpensive our energy supplies have become. Other areas where energy has a huge impact, things like medical diagnostics, whether it be X-ray, MRIs, CAT scans, etc., all very energy-intensive applications of healthcare. Of course, heating in your igloo or should I say you would be living in an igloo if you didn't have heating for your modern homes, at least up here in Indiana. Air conditioning, or the manual version of air conditioning if you didn't have sufficient energy. Things that are in our everyday lives that we hardly even think about, consuming a great deal of energy. I collected some of them here. The pharmaceuticals. You have any idea how much it costs in energy to manufacture all the medications that we use in our daily lives and to transport them to you? Appliances, dishwashers, hot water heaters, our communications, televisions, cell phones, computers, PlayStations. These are obvious, perhaps. Rock bands, not quite so obvious, but rock bands without electricity are not much fun. Manufacturing and water. We would have used up all the clean water available to us in the United States a long time ago if we didn't have wastewater treatment plants that purify our water and put it back into the system for us. So the very simple, basic requirement of clean water requires significant energy consumption. And most importantly, the lights in the stadium require a lot of electricity. So, let's talk a little bit about where our energy comes from today and has come from in the past. This is a summary of approximately 400 years of energy use in the United States and the territory that was the United States before the United States existed. And of course, the number was near zero until around 1800 when the quantity of energy starts to go up. This is in quadrillion British thermal units. I'll speak more about that unit of measure in a moment. Anyway, notice that a long time ago, a couple hundred years ago, wood was our main source of energy, and of course that was heating homes. Coal comes in starting at about 1850 and climbs steadily. Later still, we have hydroelectric power, really starting to pick up around 1900. Natural gas by probably the 1930. Petroleum in there in the 20s as well. Nuclear starts in the 60s, comes up here. Petroleum climbs over time to be our biggest fuel. Lots of things have happened, of course, during this period of time, like the development of the steam engine way back in 1782, the incandescent light bulb, which is now obsolete, and the four-stroke engine, which is still powering all of our cars today, or almost all of our cars, unless you drove here in a Tesla, all electric, or a Nissan Leaf. Otherwise, you're probably using the four-stroke engine. They come around in the 1870s. Intercontinental rail systems developed in the mid-1800s. The Rural Electrification Act, which brought electricity to homes across America, 1935. And the now famous and pretty much taken for granted interstate highway system that began construction in 1956. So all of those things are tied into our thirst for energy over the last century. Today, we are still more than 80% reliant on fossil fuels, non-renewable resources. Okay, so what do we do with them? We burn them. Simple as that. Whether it be natural gas, oil, coal, we combust them. That creates heat. We use that heat to do something useful. Very often, that heat is used to boil water. The water steam is then used to turn a turbine, which generates electricity, flows through wires to our home. But that's basically all we do with it. We burn it. We burn it in our engines, etc. So that's today. The future of energy must look a lot different. Fossil fuels won't last forever. So as we think forward, sunlight, wind, water, geothermal, biomass, all these different sources of energy, and how we store them, transmit them, and use it efficiently are in the forefront of our minds. We're going to be moving away from burning the fuel and moving more to direct conversion of different sources into usable electricity and potentially other fuels. I want to talk a bit about the different sources of energy and their uses and distribution in the U.S. and give you a view of where we sit today. To do that, I'm going to use these diagrams called Sankey diagrams. They can get a bit complicated, but they're really not bad. They're just a big old diagram with everything's moving across left to right. So energy in is on the left, energy used is on the right. And arrows and labels tell you what's going on. Okay, so here's our world today in the United States. Actually, it was a couple of years ago. The numbers for 2014 won't be available until next year. These units of energy are quad. A quad is 10 to the 15th, or 1 quadrillion British thermal units. And many of you maybe don't recall exactly what a British thermal unit is, so let me say that the typical air conditioner you would use in a medium-sized room in Indiana in the summer to maintain comfort would probably be around 10,000 BTUs, something like that. So we're going to talk in quadrillions. So here's what we use in the United States, around 97.3 quads in 2012. And it came from 28.6% from imports, 78.1% from domestic production. So here we are flowing from the supply to the consumption. We have, well, as of a few years ago, 4.6% of the world's population in the United States. We produce 15% of the world's energy and we consume 21%. So that's this imports up here. All right, let's get into a little more detail now as to the different sources of energy and where they're coming from and where they're going. Our domestic production in 2011 was 73% of our total energy need. That came from coal and natural gas. Those were the two largest contributors. After that was crude oil, nuclear electric power, and renewable energy. That's the 73% that we produce in the United States. 27% was imported, and it's all petroleum. It's not exactly true. For example, people that live in Maine buy a bit of electricity from New Brunswick, Canada, but it's such a tiny amount that it's lost in the round-off. So petroleum is the only import of significance to our total energy picture. So our supply was 108 quads, 108 quadrillion British thermal units. We consumed about 98 quads. We do export a little bit here and there, shown up here. So we consume about 98, almost, but not quite, but close to equally distributed between our homes, our residential, our businesses, commercial, industrial, and transportation. So that's the energy in and the energy out in our country today. Let's compare that to 1950. 1950, we had about half the population that we have today. We are now consuming more than 3 times as much energy as in 1950 as a nation. Our primary energy for transportation is petroleum, as it was then, but we're consuming about 4 times more now than in 1950. Primary energy for electricity generation is about 10 times more than 1950. For those of you who were around in 1950, you know why. I mean, our homes are full of electronics now, appliances and so on, that were not there in 1950. Even, I don't remember 1950s, of course. I remember the 1970s very well. And, well, I think we had a washing machine and we had a television. That's about it. Some lights. Little or no petroleum was imported in 1950. That's not the case at all today. And the amount of used and wasted energy they were in about equal proportions in 1950, but today we waste considerably more energy, 50% more than we use. I'll come back to that momentarily. Okay, so this is a little bit complicated, I understand that. It shows all the different sources of energy down the left side. solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum, these boxes are not sized proportional to how much is provided. Okay, so you would think that biomass is a major contributor, but it's not really that big in comparison to the size of these boxes. So don't worry about the size of the boxes. The weight of the lines, though, does tell you how much energy is coming from those. And over here are those same four consumptions: residential, commercial, industrial, and transportation. And, well, you can see really quite quickly where the energy sources are flowing. Petroleum, oil, is almost all going into transportation. A little bit, well, a little bit more than a little bit, but something maybe like 20%, makes its way up into industrial, and tiny bits into homes and businesses. On the other hand, you can look at electricity generation up here. How do we generate our electricity? And you can see very quickly, it's almost all from a combination of nuclear, natural gas, and coal. Those are the ones that are flowing in there, and that electricity then flows off to our homes and our businesses. Almost no electricity flows down to transportation. That 0.0257, I don't know exactly what that means. That must relate to the number of Teslas that are operating in the United States today. I guess there are a few electric-powered trains and buses around as well. Not very many. All right, so it's a complicated diagram, but it does tell you how the energy is flowing. Petroleum mostly to transportation. Everything else largely into electricity generation that then goes to our homes. Natural gas being the major exception, it bifurcates. It flows into electricity, but it also flows into heating our homes and powering our businesses as well. Okay, so this is a little bit startling when we think about electricity generation. These are the approximate numbers I showed a moment ago: coal, natural gas, nuclear power, renewable, all funneling energy in. So generating our electricity in the United States, we consume 40 quads a year. That is 40 quadrillion British thermal units, roughly 40% of our total energy use in the United States. But we're only getting 15 quads of electricity out. The other 25 quads are conversion losses, waste. So here it is flowing now to our homes and so on. So this conversion loss in our homes, in our transmission lines, and in the production facilities is very substantial. To give you just one little story that relates to that, imagine the old-fashioned light bulb, which I hope very few or none of you have in your homes anymore. I bet a few of you do. Imagine that one light bulb to whatever units you want to use. It doesn't matter, but let's say coal. And you mine 100 units, whatever they are, 1 kilogram, 100 kilograms, let's say. You mine 100 kilograms of coal, into the power plant it goes. The energy from combustion of 62 of those goes out the stacks and is lost elsewhere in the production process. Only 38% gets turned into electricity. It flows down the transmission lines. And on average, you lose about another 2%. It arrives at your home, goes into your light bulb. One of these old light bulbs, 34 units of the 36 that arrive go off in the form of heat and 2 units as light. So when you're using one of these light bulbs, you're using 2% of the electricity in the form of light that it took to light the light bulb. So they're not a very effective use of electricity. 2% of the energy. Sorry?
It's 2% of the energy of the energy input, not the electricity input.
Yes, you're right. It's 2% of the original energy content of the coal that was burned. It's not 2% of the electricity, it's higher than that. But it's not so much higher, it's 6% or so. So, just to make sure you've got that point, 34 units of heat, 2 units of light. So these light bulbs are pretty good space heaters. Not very good at generating light. So do you have any idea how many of these are in your home? And hopefully when we speak next, it'll be a smaller number than it is today. So here is the evolution of the light bulb. So here's the bulbs I had in my home 10 years ago. Let's say they're a 100-watt bulb. They're the standard, got a tungsten filament in them, passing a current through, generating all kinds of heat. You know, you had to turn these guys off like 10 or 15 minutes before you could change them if they were still working, because they were so hot you couldn't touch them. Lifespan of around 750 hours. That's your energy that goes out in light, and that's all the wasted energy. The halogen light bulb came along. It's a little bit better, but not so much. The compact fluorescent, which most of you probably are using today, substantially better. Now using about 23 watts instead of 100 to produce the same amount of light, much longer lifetime. And the best yet is the LED, which has the lowest waste and the longest life, but are still expensive. But it's not as bad as that. This was a slide from a couple of years ago. I checked on Lowe's this morning, and you can get yourself a 60-watt equivalent light bulb LED for $7. It'll pay for itself pretty quickly, because you'll never have to replace it again, unless you use it all the time. Then maybe you'll have to replace it in 20 years, and it'll use far less electricity. So we think about how much electricity we're going to need, or how much energy, rather. I want to broaden the conversation back to energy in general, not just electricity. How much we're going to need in the future? Well, we know how much we've used in the past. The OECD countries are the developed nations that are believe in a market economy. So Canada, United States, Britain, much of Europe, etc. The energy use in these developed nations hasn't really grown that much, relatively, over the last century. It is growing, and it will continue to grow. But the big growth will be in the developing nations, right? That's where a lot of people live almost energy-free lives, and they don't like it. And think about sitting around the fire and riding a horse to work. That's where you're at. It's hard, of course, to predict what's going to happen in the future, but this is one set of projections. That's the source. We go out even a little bit further from the IPCC predictions, and we could be up to 1,286 quads worldwide. So we must start to wonder, how is this going to be met? How are we going to get there? So we need to understand a little bit about how we got where we are and how long things may last. So this figure is from the federal government. It tells us how much of the different sources of energy we've used in the last 30 years. Petroleum, so that's all the oil, coal, nuclear, liquid biofuels, renewables, natural gas. And what you see is, well, they've all been fairly constant over the last 30 years. Natural gas is picking up a bit of a bigger slice. And then you project forward to maintain our lifestyles in the United States. This is the kind of growth we're going to need. And then you wonder, okay, well, that's 30-something years, 26 years. Do we have enough of these different sources to get us here even? Interesting question. So let's take a little look at that. So here are the major energy sources in the U.S. Renewables, nuclear, coal, petroleum, and natural gas. Let's look at the fossil fuels first. These are the current predictions regarding the reserves of these fuels on planet Earth, divided by different countries. So the OECD, the non-OECD, the European Union, former Soviet Union countries, and the whole world. And the number is actually the amount we use per year. It's the total number available, we think is available, divided by the amount we use each year. So these are years. So you can read that. Okay, we got oil, natural gas, and coal. So natural gas in the United States, that looks like it's 15 or maybe 20 years, right? Now we can debate whether we're going to find more or not, or how much more, and so on. But regardless, we have to face the reality that oil and natural gas are far from being infinite resources. And in many of our lifetimes, they're going to become prohibitively expensive. On the other hand, coal is abundant in the United States and elsewhere, and we could rely on that for several more centuries. The biggest thing that's happened in fossil fuels is fracking, hydraulic fracturing. It was really a game changer in natural gas in the United States. It's become a fairly controversial topic. It's been responsible for providing pretty cheap electricity and other forms of energy to our homes for the last several years. Natural gas production from conventional sources peaked in 1970 and has been in steady decline ever since, until recently when the unconventional started to skyrocket. This only goes to 2008, right? If we went out a little further, you'd see this nipping way up here, and that's natural gas from fracking. This gives some projections. Here we are in 2011. This is fracking gases from shale, so it's also called shale gas. These are different types of natural gases, and you can see the prediction over the next few decades how shale gas will become a bigger and bigger commodity, a bigger and bigger part of the total natural gas. This is a schematic of a geologic formation. So the way to think of this is you got the land surface, so here you're sitting up here somewhere. The rocks are bent, so they're wavy. You've got different units of rock, sandstone, shale. Maybe this is another shale of some sort here, whatever. And then you have your different forms of fossil fuels. The fossil fuels in here, of course, are due from prehistoric life, are due to prehistoric life. The coal beds are due to swamps that were buried and have gradually been converted through peat to coal. The gas and oil down here are due to mostly marine microorganisms that died a long time ago and have been converted. And both the oil and the gas are lighter than water, so they tend to flow upwards. So this is our source rock here, and to some extent here in the sandstone. So the oil and gas have flowed up, and they've become caught in these different traps underneath this impermeable rock. And then we can just drill in there, and out comes the gas. It's under its own pressure. Here or over here, we can get some oil. That's what we call conventional natural gas. That's the stuff we used that peaked in 1970 production-wise. Coal bed methane, a little bit up there, a little of this tight sand gas. But the fossil fuels that we're after here all come from this organic rich shale down here. But a lot of them never get out. So fracking is a process where a well is sunk into the geologic unit, then the course of the well drilling is changed so that you drill along through the unit, then you inject fracking liquid, which is most often water, with additives that open up the porosity in this rock and allow the gas to escape, to be recovered. So that's what's going on today. By the way, heard a fellow say this last night, that's kind of the last corner of the warehouse of fossil fuels when it comes to natural gas. We've already consumed the easy stuff. And now we're down to the birthplace, if you like, of the natural gas, pulling out what's left. And it won't last forever. We can debate how long, but it's decades, certainly not centuries. Nuclear. Well, nuclear was probably the most promising new form of energy ever. Vast quantities of cheap energy from small amounts of fuel. And everything went pretty well until the 3 Mile Island accident here, I think it was 1979. The number of units ordered peaked, construction permits leveled out. Reactors that were running at the time of 3 Mile Island largely continued, but no new reactors were built. The result, of course, is that the energy produced leveled right out. It didn't quite level out, it actually went up a little bit because the efficiency and uptime of the different units was improved over time. But because of a change in public opinion, which historically seems to be mostly attributable to the 3 Mile Island incident, many of the plants that were planned never got built. Right now, we have 104 that are operating. They produce 20% of our electricity in the United States. There are issues, of course, with nuclear. I'm happy to discuss those at some length if you want later. But right now, I can tell you that technologically, we can still greatly expand nuclear if we choose to do so. And there's ample fuel using the best technologies available to meet our needs for a long period of time. Other countries have done this. We lag behind. France is the world's leader in nuclear power, producing 80% of their electricity with nuclear reactors. And then you go through all this long list of countries, eventually arriving at the United States. The United States, however, it does have the most reactors. It just happens we have a lot of people and a lot of energy consumption. So we have the most reactors, but we do not even come close to producing the largest percentage of our electricity with nuclear. And then renewables. Renewables are anything that basically should not run out with time, anything that we can rely on being here for future generations. Hydroelectric power, dams. We have a nice one in Mishawaka, neighboring city to South Bend. That's where most of my own home's electricity comes from. Wood burning, various types of biofuels, corn or whatever, wind, geothermal, and solar panels. Those are what we currently consider to be our list of renewables. Right now, producing approximately 9% of the electricity, or the energy rather, in the United States. And most of it, the biggest portion is from hydroelectric. Second is wood. Biofuels has climbed some, and then we get down here. Wind is climbing, but it's still a very, very small amount of the total. And the main problem with using renewables like wind and solar, and even hydrothermal for that matter, is location. Here's our planet, or no, it's not our planet, it's, pardon me. Here's the United States of America, and a little bit of Canada up here, that's where I grew up, right over there. And this is probably from NASA, taken at night, so it shows light pollution, which is a good indicator of where energy consumption is taking place. And, well, you know, you guys are from all over the place. You only just gathered here for this football game. Although most of you probably spent time in Indiana as students, or are students today. But, you know, here's the windy part of the United States, to a large degree, the Dakotas and stuff. And here's the sunny part of the United States, down here in the U.S. Southwest. So the wind and the sun, but unfortunately the demands are not there, they're on the coasts. And this is a really big challenge in the United States. We could harvest much more energy from sun and wind in these regions, but how to get it here, or how to get it here? Transmission is expensive in and of itself. So, you might have heard that there are some environmental issues associated with energy. So I thought I'd mention those. There are a few Time magazine or Newsweek articles that point to this problem. Actually, there are lots of articles. You all know about it. Global warming. So scientists like me, we have open minds on issues such as global warming. We see it as a valid scientific theory, and we want to understand better. We want to collect more data, think more deeply, revise our theory, and so on. So to really understand global warming, CO2 emissions, and the link between them, we really have to understand the whole Earth system, how the Earth's land, water, air, and life all interact to form the planet we live on. And it's really far from simple. But there are some pretty simple facts that we can rely on. One of them is the measurements of carbon dioxide in the atmosphere that have been collected since before 1960 on Mauna Loa in Hawaii. You all know where that is, of course. Hawaii's out in the middle of the ocean. It's not near a major industrial center or anything that would be causing a local perturbation. So it's thought that this gives a pretty good representation of how the CO2 levels in the atmosphere have changed through time. And we know in the old days, prior to around 1800, it was around 280 parts per million. So if you gathered 1 million parts of air, 280 were CO2. And they have increased. There's a seasonal variability, winter, summer, that's why there's this up and down. But there's been a steady increase over time. And now, some measurements have put it a little over 400, but we're probably on average right around 395 ppm CO2. I think we can all agree that this CO2 has come from burning fossil fuels. There are a few other sources that one could imagine, but none of them are legitimate. And we know we burn the fossil fuels. So this is not a point of argument. This has happened. The questions one might ask are, well, how unusual is this? And is it something we should be concerned about? I'm a geologist by training, so I spend a lot of my time studying past Earth. There is 4.5 billion years of Earth history to consider, for example, and the last 30 or 40 years is a pretty trivial amount in comparison. So we look at the rock record. We study fossils, we study indicators of climate in the past and so on. But it turns out a pretty special kind of rock has given us some of the best insights into the variation of CO2 and other gases in the atmosphere over the last nearly 100,000 years. And that's a seasonal rock here in these parts of the world. It's called ice. Ice is a rock, it just happens to melt in the summer. And so, international scientific teams have taken ice cores through ice in the Antarctic back through time. It snows, you get a new layer on each year and it gets compacted. So as you drill down through one of these ice cores, you're going back further and further in time. The ice gets older and older as you go. And that ice contains air bubbles. So if you're careful, you harvest the ice properly, put it in proper frozen containers and ship it to your lab and extract the gas, you can actually directly measure what the CO2 gas in the atmosphere was in the Antarctic back through time, back to around 800,000 years ago. And this is the record. Well, years before 1950s here, and then this is modern times after the fossil fuel burning started to really add a lot. So, go back 800,000 years of ice records that have been analyzed. This is methane here, this is carbon dioxide here, and this is the temperature, which can be measured by isotopic ratios in the same gas bubbles. Very interesting. So methane is a very potent greenhouse gas, CO2 is not quite so much, but they all track together. Where the temperature goes up, these gases are going up. Where they come down, the gases go down. And, well, we can argue exactly why that's the case. But over 800,000 years, they've never gone much higher, well, than 300 parts per million. And now we're about to break 400. How much does that matter? Well, good question. Oh, you're probably wondering why there's all this cyclic variation. That's explained by variations in the Earth's orbit. The centricity, the obliquity, and the axial precession, and when they're all averaged together, they give this kind of this specific type of pattern. So it seems totally natural, totally natural. But the recent additions we've made are not natural. They're something different. So the question you might ask is, does this matter? And, well, I'll tell you what, we're running the experiment right now. It's going to be another few decades before we have a clear answer on how much it matters. But we're running the experiment, that's for sure. There are a lot of different models on how much CO2 will be accumulating in the atmosphere over time. There is not scientific consensus as to the magnitude of the problem, but everybody agrees it's going to increase. We have the data from Mauna Loa and a few other places through time, and here we are now sitting up about here at around 400. Where's it going to go in the future? Well, there's many different models based upon all kinds of different assumptions, and they have big bands. These represent the uncertainties in the model. So you can see there isn't scientific consensus on where it's going other than it's going up. And then you can debate how big the impact's going to be. It's a really complicated system, our planet, and carbon. This just summarizes some of it. Soil has carbon in it. Bacteria, they chomp up carbon, they chomp up CO2, they release gases. Of course, we have our fossil fuel burning. Trees are out there respiring CO2 and releasing oxygen in photosynthesis. Soils absorb. There's fossils that have lots of, it's everywhere. In the oceans, a great deal of carbon dioxide is dissolved in the oceans, and the oceans don't circulate up and down that fast. So there's layering, and it just takes a long time. Extraordinarily difficult and complex system to understand. But the theory is pretty straightforward and quite robust. This shows incoming solar energy that's delivered to our planet from the sun. Obviously, it depends on lots of factors, including cloud cover. Depends where the light hits. Some of it's reflected back into space. Some of it gets absorbed by the surface. If the surface happens to be covered with snow, more of it will be reflected back. But what we're messing with is this area right here, the greenhouse gases. They are basically an insulation, a blanket around the planet. They've always been there. There's always been a greenhouse effect. Thank goodness, otherwise it would be one hell of a winter in Indiana. So they've always been there, but the balance has been such that our temperature is around what it has been or colder. When I was here 20,000 years ago, I had to chip my way down through 2 to 3 kilometers of ice to get to the lecture theater during the last ice age. Fortunately, it's retreated. If that ice starts to come back, I'm all for moving this campus to California, Arizona, maybe Mexico, because this will not be a good place to be. But anyway, greenhouse gases, like this blanket around the planet, and we're adding more and more blanket. I don't know how bad the problem is going to be. I don't know how much this is going to affect our children and grandchildren and great-grandchildren's lives. But it is cause for considerable concern, okay? And the reason is because all that solar radiation coming in, much of it has to go back out, but the greenhouse gas blanket that we're adding to insulates it and keeps some of it in. So here's some scenarios that have been presented by this IPCC. They've been heavily criticized by some sectors of the society, but it is what it is. It's a bunch of predictions. And they assume that we stop burning fossil fuels soon. Pretty much all the arguments, models that have come out indicate, well, we've already done a lot of the damage. Even if we stop burning fossil fuels in the next few years, we're going to continue to see a rise in sea level. We're going to continue to see a rise in temperature for perhaps a couple centuries, and CO2 levels won't come back down for a very long time. So it is worrisome that if we are causing this problem, it's not going to go away. So it's interesting to think about what we could do about that in the future of energy in the US and elsewhere in the world. And it's an extraordinarily complex thing to contemplate. So many assumptions have to go into the future. Economic growth, population growth, different types of fuels, costs, etc. There are many different predictions. Here are 3 of them. These are 3 predictions for energy consumption across the different energy sources in the United States going forward in time out to a little past 2100. And what you see, the conventional things, burning oil, burning natural gas, burning coal, nuclear, biomass, and renewables. These are different scenarios. We're at about here today, right, at around 100 quads. So this scenario doesn't see that much energy growth. Everything stays about the same. This one here sees a big increase in coal and a significant increase in energy use, and presumably oil and natural gas run out and become more and more expensive, so coal's piece of the puzzle goes up, or piece of the, not the puzzle, but the pie. Or in this one, our energy use goes up even further. Coal and oil are the biggest contributors, natural gas having just about run out. This one, of course, assumes that many new oil discoveries will be made. So you can see that it's impossible to know what the future brings, but one can come up with several scenarios, kind of bounding scenarios, let's call them. Now, let's impose on those that we don't want the CO2 in the atmosphere to go above 450 parts per million. We've decided that that's a critical level for some reason. I don't know why, but let's say we did. Of course, the United States couldn't do this alone, but the United States parts in it would look something like this. So these are vastly different scenarios compared to up here. They're so, it's hard to see them. So let's move on to a bigger version. So this is, I'm going to look at this one scenario here, the merge scenario. So to remind you, we've got oil declining, natural gas declining, coal increasing because that's the one thing we can be sure of, biomass, nuclear, renewables. All of them increase a little bit, as does our use. Now, if we want to keep CO2 no higher than 450 ppm, and assuming that other nations in the world cooperate and have such a view, what do we have to do? Well, it gets really ugly fast, doesn't it? We've got to reduce our energy consumption by that much. We've got to have renewables in here. We've got to have much bigger nuclear than we have today. We've got to have a much bigger biomass. We've got to sequester the CO2 from coal burning and dispose of it. And natural gas and oil are almost gone. And if we, well, that's what the future will hold if we wish to achieve this. So just a few words now on some things that we're doing here at the University of Notre Dame that relate to all of this mess. This again is our research use, or pardon me, our energy use today, our sources and where it's going. We have three major research themes that the university has invested in the last few years. There are several other very important energy research themes as well, but I don't really have time to cover those, so let's just stick with these three. We've got a significant amount of work going on in cleaner fossil, which is CO2 sequestration, the chemical engineering behind the recovery of CO2 in the gas streams coming off coal-burning plants, the conversion of that to supercritical CO2 and the ultimate geologic disposal of it. We've got a lot of work going on in solar. We call it transformative solar, where a team largely led by this fellow, Prashant Kamat, is developing ways to get much higher recovery of the energy. The conversion rates are much too low. That's the problem with solar. The sunlight shining on the panel, most of the energy that arrives is lost in heat and other things. Very little trickles out of electricity. So the chemistry and material science that's going on is at that interface trying to up the conversion rates. Professor Kamat recently invented this stuff, which he calls solar paint. You can get it by the gallon. Well, no, it's actually not commercially available. But imagine that when it is, if you could just go out and paint your house and hook some wires on and generate a significant amount of the electricity that your house needs. That's the kind of thing that, well, we hope to achieve. The third area is safer nuclear, and that's kind of a silly title because nuclear has been extremely safe in the United States, even including the 3 Mile Island accident. But aside from that, when we talk about safer nuclear, we're talking not only about the operation of the plants, but the environmental impacts of mining, the safe ultimate disposal of nuclear waste in a deep geologic repository, the safe recycling, etc. And we have a team of researchers here that have been developing a new family of nanomaterials that are totally unique to Notre Dame. These things came from here specifically and have been developed here over the last decade, and they have great potential in significantly improving the fuel cycle, especially at the back end, which is where recycling of fuel can take place. So that's only a very small snapshot of some of the research we're doing at Notre Dame to try to help secure our energy future. There's lots of work going on in wind engineering, geothermal, biomass, reduction of consumption, things like sewage treatment plants. How do you reduce the amount of energy you're using there? And communications and so on. It's far more than I could cover today. But I wanted to give you a sense of where we are, what the problems are, and what we hope to do about it. And I thank you very much for your attention. And I'd be happy to take questions. Yes, sir.
Yes, please. With China and India, they're using more fossil fuels for airplanes. When do you really feel we're going to run out of petroleum? When do we run out?
Well, we apparently ran out last year. I mean, if I looked when I was a kid, that was the prediction. And so as we move through time, more and more reserves have been discovered that were unknown. Technologies for recovery have improved. So when, I don't know. The current prediction is it's always 20 or 30 years out. Is it 20 or 30 or 60 or 100? I'm not sure, but it will happen. It's not a renewable resource. Well, it is, but you have to wait some 50 million years. So from our perspective, it's not renewable, so it will run out. And as it does, of course, the cost will skyrocket. Yeah.
Can you explain the enormous contradictions that we hear from the scientific community, depending on which scientific community is making this projection? For example, the ice in both the Arctic and Antarctica, we were told initially was receding. But later studies now show it's actually expanding. So how do we get these two sides of the brain to get together and say, give us a picture that we can reasonably...
Well, I've personally seen glaciers in the north of Canada, which I've visited repeatedly over 20 years, and they are definitely receding. But that's a local observation. It doesn't say that all ice on Earth is receding, and there are definitely some glaciers that are advancing. It's very complex because the rate of advance of a glacier or retreat is not really so much due to the temperature where the end of the glacier is as the climatic conditions where the glacier begins. So if snowfall goes up and it gets a little colder or even a little warmer, if snowfall goes up in the zone of accumulation of the glacier, it will expand. So even a warming of the climate could trigger expansion of glaciers in some scenarios. But to get to your point, I'm really saddened by the politicization of the science in our country, where the debate over the use of fossil fuels and global warming and so on has kind of split right down the political middle. And, you know, there are exceptions, of course, but it's become very politicized. And I think it would be far superior to seek the facts, you know, and really try to understand what are we doing to the planet and is it a big deal? So I think, I'm not sure if I answered your question, but I know there was someone here. Yes, sir.
If this country was able to go nuclear, how many nuclear plants would it take to supply the major areas? Maybe you wouldn't hit all the outlying areas, but I know in Georgia there's 2 big nuclear plants being built right now, down near Savannah.
Yeah. But to meet all the electricity needs of the United States would take 500 approximately. Right now we have a little over 100, so about 5-fold increase. Yes?
So, you know, the chart you showed of the United States shows most of the consumption happening on the east and west coast. And one of the renewables that wasn't mentioned there would be tidal. Mm-hmm. Where does that stand in the pictures? It's so small and so underfunded that it just isn't explored.
Well, right now it provides nothing. Well, maybe it's not quite nothing, but it's so close to nothing that it doesn't make it on any of the charts. There are some places where I'm not up to date on the latest technologies, but I do know there are some places like the Bay of Fundy between Maine and New Brunswick where an absolutely huge amount of water goes in and out twice a day. And so locations like that have great potential for tidal electricity generation, but it's not been developed yet. It's been just debated for 30 or 40 years. Other places with nice straight coastlines and stuff, it would be much harder to execute. Another opportunity is offshore wind development, where you could put offshore platforms several kilometers out in the ocean and generate electricity from the wind, where it would be much more consistent. Even off New York, you'd have lots of wind if you went out far enough, and you wouldn't have to face the problem of transporting wind energy from South Dakota to New York. So there are a lot of different possibilities. I'm a little hesitant to tell you this, but I'll tell you anyway. What's the worst that could happen? I think the all of the above strategy of the current federal administration is a bad one. It's a cop-out, right? And we've been copping out of our energy issues for decades in the United States. I think we should have a national energy policy that should be based upon sound science and engineering and economics and whatever else, ethics, et cetera, that come into the story. And we should, our government should figure out what this thing is, our representatives, and that it should become our policy, and it should stay pretty consistent through time. But what we do have is a totally capitalist-driven system where changes in commodity prices have big impacts. So 10 years ago, 30 new nuclear plants were in the design and licensing stage. Only 2 of them are being built. Had nothing to do with Fukushima, which is the common perception. Fukushima didn't impact the American industry at all. It was the price of natural gas. When fracking became a big deal and the price of natural gas plummeted, utilities no longer have a need to produce with nuclear. So 28 plants were gone. But is that the best thing for us as a nation for the next century, to be relying on that natural gas today? I think we need to have that discussion, and we need to have a policy, and I think we've got the best scientists and engineers on the planet. If we had a clear target on the wall, let's say 2050 or 2030, 2025 even, and we knew where we were going, I think we'd get there. But we don't know where we're going. So that's my 2 cents worth. Yes, sir. Yeah.
I was just going to say, I'm thinking mass population like myself, I'm afraid of nuclear because we just think of the word nuclear, so we don't want nuclear plants in our backyards.
Yeah.
Is it misinformation?
Absolutely. My expertise is in nuclear, and there are a lot of reasons why that's the case, and the association with nuclear weapons and nuclear winter and all that is a part of it. But I can tell you that in the United States, the nuclear industry has been superbly safe and produced vast amounts of electricity, including what's coming out of the lights right now, by the way. In all likelihood, it came from the Cook nuclear plant up in Lake Michigan. I visited these plants. They're beautiful, clean, safe facilities. But yes, accidents can happen. We're only human. The designers are only human. Things happen that were not expected. But you have to measure the magnitude of that versus the benefit. I would argue nuclear is a very good option, but it's not my decision. It's of course yours and all the rest of the voters in the United States to hopefully move us towards some kind of a, if I had to choose something right now, I would probably say 2030 we need to be 1/3 renewable, 1/3 fossil, 1/3 nuclear. And we're going to spend whatever money we have to do to get there, and we're going to pay for it. That would be, if I had to make a policy at this moment. That's an oversimplistic approach.
Great. Thank you very much, Peter, for joining us today.
Thank you.